In this next set of videos, I'd like to tell you about a problem called anomaly detection. This is a reasonably commonly used type of machine learning, and one of its interesting aspects is that it's mainly thought of as an unsupervised learning problem, but there are some aspects of it that are also very similar to sort of a supervised learning problem. So what is anomaly detection? To explain it, let me use the motivating example of imagine that you're a manufacturer of aircraft engines, and let's say that as your aircraft engines roll off the assembly line, you're doing QA, quality assurance testing, and as that part of that testing, you measure features of your aircraft engine, like maybe you measure the heat generated, things like the vibrations, and so on. I actually have some friends that worked on this problem a long time ago, and these were actually the sorts of features that they were collecting off actual aircraft engines. And so you now have a data set of X1 through XM if you have manufactured M aircraft engines. And if you plot your data, maybe it looks like this. So each point here, each cross here is one of your unlabeled examples. So the anomaly detection problem is the following. Let's say that on the next day you have a new aircraft engine that rolls off the assembly line, and your new aircraft engine has some set of features X tests. What the anomaly detection problem is, we want to know if this aircraft engine is anomalous in any way. In other words, we want to know if maybe this engine should undergo further testing, because or if it looks like an okay engine and so it's okay to just ship it to a customer without further testing. So if your new aircraft engine looks like a point over there, well, that looks a lot like the aircraft engines we've seen before, and so maybe we'll say that it looks okay. Whereas if your new aircraft engine, if X tests, were a point that were out here, so if X1 and X2 of the features of this new example, X tests were all the way out there, then we would call that an anomaly, and maybe send that aircraft engine for further testing before we ship it to a customer, since it looks very different than the rest of the aircraft engines we've seen before. More formally, in the anomaly detection problem, we're given some data sets, X1 through XM of examples, and we usually assume that these M examples are normal or non-anomalous examples, and we want an algorithm to tell us if some new example X test is anomalous. The approach that we're going to take is that given this training set, given the unlabeled training set, we're going to build a model for P of X. In other words, we're going to build a model for the probability of X, where X are these features of, say, aircraft engines. And so, having built a model of the probability of X, we're then going to say that if for the new aircraft engine, if P of X test is less than some epsilon, then we flag this as an anomaly. So we see a new engine that has very low probability under our model P of X that we estimate from the data. Then we flag it as an anomaly. Whereas if P of X test is, say, greater than or equal to some small threshold, then we say that okay, it looks okay. And so given a training set like that plotted here, if you build a model, hopefully we'll find that aircraft engines, hopefully the model P of X will say that points that lie somewhere in the middle, that's pretty high probability, whereas points that are a little bit further out have lower probability, points that are even further out have somewhat lower probability, and a point that's way out here, a point that's way out there would be an anomaly. Whereas for a point that's way in there, right in the middle, this would be okay, because P of X right in the middle of that would be very high, because we've seen a lot of points in that region. Here are some examples of applications of anomaly detection. Perhaps the most common application of anomaly detection is actually fraud detection. If you have many users, and if each of your users take different activities, maybe on your website or in a physical plant or something, you can compute features, xi, of the different users' activities. And what you can do is build a model to say, what is the probability of different users behaving different ways? So what is the probability of a particular vector of features of a user's behavior? So, examples of features of a user's activity may be on the website, it'd be things like maybe X1 is how often does this user log in? X2 maybe the number of web pages visited or the number of transactions. Maybe X3 is the number of posts of the users on the forum. Feature X4 could be what is the typing speed of the user, and some websites can actually track that. So what's the typing speed of this user in characters per second? And so you can model P of X based on this sort of data. And finally, having modeled P of X, you can try to identify users that are behaving very strangely on your website by checking which ones have probability of X less than epsilon, and maybe send the profiles of those users for further review, or demand additional identification from those users or some such to guard against strange behavior or fraudulent behavior on your website. This sort of technique will tend to flag users that are behaving unusually, not just users that may be behaving fraudulently. So not just accounts that may have been stolen or users that are trying to do funny things, or just find unusual users. But this is actually the technique that is used by many online websites that sell things to try to identify users behaving strangely, and that might be indicative of either fraudulent behavior or of accounts that have been stolen. Another example of anomaly detection is manufacturing. So already talked about the aircraft engine thing, where we can find unusual, say, aircraft engines and send those for further review. A third application would be monitoring computers in a data center. And I actually have some friends that work on this too. So if you have a lot of machines in a computer cluster or in a data center, you can do things like compute features of each machine. So maybe some features capturing how much memory used, number of disk accesses, CPU load, as well as more complex features like what is the CPU load on this machine divided by the amount of network traffic on this machine. Then, given a data set of how your computers in your data center usually behave, you can model the probability of X. So you can model the probability of these machines having different amounts of memory use, or probably of these machines having different numbers of disk accesses or different CPU loads and so on. And if you ever have a machine whose probability of X, P of X, is very small, then you know that machine is behaving unusually, and maybe that machine is about to go down, and you can flag that for review by a system administrator. And this is actually being used today by various data centers to watch out for unusual things happening on their machines. So that's anomaly detection. In the next video, I'll talk a bit about the Gaussian distribution and review properties of the Gaussian probability distribution. And in videos after that, we'll apply it to develop an anomaly detection algorithm.